5.1 derivatives of exponential functions, y equals e to the x. Okay, another type of nonlinear model is the exponential function y equals e to the x, which are used to model rapid change. Examples of exponential functions are compound interest, population growth, intensity of an earthquake, or like radioactive decay. Okay, so specifically when we have the base, so this is usually called b, right? When we have the base of e is actually a number, it's Euler's number, and it is approximately 2.718. If you were to take your calculator out and put e, and then it's going to ask you for a number, and you put 1, like e to the exponent 1, it's going to give you Euler's number, but like the longer form of it. Okay, it's irrational. It's going to go on forever. It's very, when you think of e, think also of kind of like a pi, where it's like 3.141598, whatever it is. Okay, so same idea, it's just an e. Okay, so here are some properties of e to the x, and I just want to highlight, so far we've graphed functions in advanced functions and in intro to functions, like 2 to the x, we've graphed 3 to the x, we've graphed, say, 4 to the x, and so on. We've graphed all of these numbers, even maybe 1/2 to the x. Okay, we've graphed all of these exponential functions. E to the x is no different. E to the x is just simply the base. Instead of the base being 2, it's now 2.718. Okay, so think of it as exactly the same. So all of the algebraic calculations that you would do, say for example for e to the x, would take on the same laws as 2 to the x, 3 to the x. Okay, so since y equals e to the x is an exponential function, it has the same properties as other exponential functions. The function y equals e to the x has an inverse of this. Y equals log base e to the x. Okay, and this function is whose graphs are reflections in the y equals x line. Okay, so we know that this inverse line, this green line right here, is the line y equals x. And for the inverse, these are reflections on either side of that line. So all of these points are going to be equidistant from this line. Okay, every single point on e to the x is going to be reflected as, what we do is we call it ln x. So the function y equals log base e to the x actually means just ln e. Sorry, switch this to ln x. Okay, so y equals log base e to the x, x equals ln x. Okay, so these two are equivalent. And this is called, ln x is the natural logarithm function. That's what it's called. Okay, so let's take a look at these two graphs here. Okay, so this is, we're going to look at the graph y equals e to the x, which is the blue one here. And then we're going to look at the graph y equals ln x, which is this red one here. Okay, so as you can see, the domain of e to the x, it extends in both directions. Like this does, like even though this looks like it's kind of going vertical, it's not approaching an asymptote, so it will eventually extend to infinity forever. Okay, and then the range, of course we know that there's this horizontal asymptote, okay, in the form y equals 0 as the base one, right? No transformations on this. So y is strictly greater than 0. Y is never going to hit 0. It is a horizontal asymptote, okay? And then when we look at the comparison of the domain and range to the inverse function, we know that the domain becomes the range and the range becomes the domain. So XER, so our range for the red function here would be YER. Okay, we go down forever and we go up forever. Again, there's no asymptote here that this approaches. It looks like it's going to eventually go horizontal, but it doesn't. It's going to extend up to infinity forever. And then the range, now for ln x, we have this vertical asymptote, oops, okay, of in the form x equals 0. Okay, so just like any other exponential function, this y-intercept right here, the function passes through 0, 1. And because ln x is the inverse function, we would switch the x and the y. So then we know one of the points for sure is 1, 0. So 1, 0, which is right here. Okay, so this would be like the y-intercept. This is actually the x-intercept. Okay, because those switch. Now, e to the ln x equals x, because e and ln basically cancel out, okay, when x is greater than 0. And then ln e to the x, again, these cancel. X equals x, that makes sense, for x is a real number. Okay, and the line y equals 0 is the horizontal asymptote. The line x equals 0 is the vertical asymptote. Again, this one and this one as inverses, that makes sense because they would switch. They would reflect in the x equals y line. Okay, so now the derivative of f at x equals e to the x is actually f prime at x equals e to the x. That's it. That's the derivative. So the derivative of the function is the function itself. Okay, so let's do a little bit of an investigation. We're going to find the first 4 derivatives of f at x equals e to the x. So I was thinking about going across. I'm going to list them. So we have f at x equals e to the x. Well, the derivative of e to the x is e to the x. Now for the second derivative, we find the derivative of the first derivative. So the derivative of e to the x is again e to the x. And the third derivative of e to the x, we would find the derivative of the second derivative, which is again e to the x. And the fourth derivative, f prime 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 prime, would be the derivative of e to the x, which is e to the x. So the first 4 derivatives of f at x e to the x is the same, e to the x, okay? And for the next 100 or 1,000 thereafter. Example 1, determine the derivative of f at x equals e to the 3x. So this is a little bit different because in the exponent here, it's no longer just x. We're now actually talking about a composite function. So if we take a look at this box down here, the derivative of a composite function involving e to the x. So in general, if f at x equals e to the g to the x, okay? So basically, if this is no longer x and this is actually a function, then what we have to do is, for the derivative, it's e to the g to the x, which is the same thing, right? So rewrite your function. Then we just do the chain rule. Then we do the derivative of the exponent there. And that's it. So the long way of this, so f at x, f prime at x is going to be d by dx of e to the 3x, which is going to be, we're going to rewrite e to the 3x, because that's the derivative of this, but then we still have to derive d by dx, we still have to derive 3x, because that is the function there. So f prime at x equals e to the 3x times the derivative of 3x is just 3. Okay, and to rewrite this, I would just take the 3, put it in front. I would write this as 3e to the 3x. Okay, so determine the derivative of each function. This is example 2. So let's start with A. I'm going to just rewrite this. G to the x equals g at x equals x squared minus x. Okay, so this here is our secondary function. So we're going to do g prime of x equals, we're going to write this entire term as it is. As soon as you see that the base is e, just rewrite it. E to the x squared minus x times, right? We're going to do the derivative of this exponent. So derivative of x squared, you bring that down, we get 2x. Then the derivative of negative x, when it's x, you just take the coefficient, so negative 1. So we can either write it like this, or we can distribute this in, and it would be 2x e to the x squared minus x minus 1 e to the x squared minus x. Okay, this one's factored. This one's just expanded. Same thing. Okay, so I'm going to rewrite b now. Okay, so I get f at x equals x squared e to the x. All right, so taking a look at this, we have two separate functions that are multiplied by one another. Okay, we have x squared, then we have e to the x. So if we call this u and we call this v, we know that the derivative of uv is the derivative of u times v plus the derivative of, or u times the derivative of v. So let's apply product rule. F prime at x. So derivative of x squared is 2x. We're going to now just write e to the x. That's it. Plus u as it is, which is x squared. Now the derivative of e to the x is just e to the x. So we can either write it like that, or we can factor out the e to the x, and an x. Okay, so if we factored out an x e to the x, we'd be left with 2 plus x. Okay, and I would switch these around just for better form. So our answer would be x e to the x, x plus 2. Okay, again, this is factored afterwards, and then this is just like the expanded version. The expanded version just simply after product rule. Example 3, given f at x equals 3e to the x squared, determine f prime at negative 1. Okay, so the first step is to determine f prime. So we're going to take f at x. We're going to find f prime at x. It's right here, so I'm not going to rewrite it. So we know the constant rule. So just to remind us of the constant rule, if we have a constant times f at x, and we want to find the derivative, it would be like the constant times the derivative of f at x. So essentially, we can just pull the constant out, bring it down, and then find the derivative of f at x. So that's what I'm going to do. I'm going to pull this 3 down, and I'm going to leave it. And now I'm going to find the derivative of just solely e to the x squared. So derivative of e to the anything, we have to rewrite it as it is. Then we notice that the exponent is not just an x, it's an actual function. So let's multiply that by the derivative of x squared, which is 2x. So if we wanted to go ahead and simplify this, 3 times 2 is 6. I would put the x in front of the e. So we get 6x e to the x squared. So we went ahead and found the derivative. Now let's plug in negative 1. So f prime at negative 1 equals 6 negative 1 e to the negative 1 squared. Okay, 6 times negative 1 is negative 6. And then we have e and -1 squared is just 1. So it's -6e or -6e to the 1. Either one works. Okay, now example 4. Determine the equation of the tangent to y equals e to the x divided by x squared, where x equals 2. Okay, so the first thing that we need to do is we need to find the derivative, which is like the slope. Okay, derivative. So I'm going to rewrite this as y equals e to the x times, instead of x squared, I'm going to move the x squared to the numerator. And what happens when you move it to the numerator is the exponent changes sign. So it's going to be x to the -2. Let's call this u, let's call this v. We know that this is product rule. So uv prime is going to be u prime v plus uv prime. Okay, so y prime, the derivative of e to the x is e to the x times v as itself, so x to the -2, plus u as it is, which is e to the x, times the derivative of v. So we're going to bring it down that -2. We're going to multiply it by x to the -3, because that's -2 minus 1. Okay. So let's just simplify this a little bit more. I get e to the x, x to the -2, plus e to the x. No, I'm going to put the -2 there first. I'm going to bring this over here. -2, e to the x, x to the -3. Okay, so this is the derivative. Now, if we're solving this when x equals 2, what that means is we're going to sub in y prime at 2. So we're going to go ahead and sub in 2 everywhere where there's an x. So e to the 2 times 2 to the -2 minus 2 e to the 2. Oh, that's 2 to -3. Okay, so I'm going to keep e to the 2 as e to the 2. Now, 2 to the -2 on the side of my paper, I'm just going to put, I'll put up here. 2 to the -2 is like saying 1 over 2 squared, which is 1 over 4. Okay, so this first term is e squared over 4. Now we have minus 2e squared, and then we have 2 to the -3. So 2 to the -3 is like saying 1 over 2 cubed. And I get 1 over 8. 2 and 2 is 4, 4 and 4 is 8. So this is going to be over 8. The 2 and the 8 cancel out. The 8 goes to a 4. So I get e squared over 4 minus e squared over 4. So I get 0. The slope of our tangent line is 0. That means we have a horizontal tangent. If we think about what that means in regards to, like, for example, y equals mx plus b, we think about that, we're going to have y equals 0x plus b. So this term is going to go to 0 regardless. We would sub the 2 in here, but it doesn't matter, okay? So we're going to go y equals b. What we need to do is we need to solve for the full coordinate, x equals 2. We need to solve this for x comma y, which is going to be 2 comma some other number. And we just sub that 2 into the original. So y equals e to the 2 over 2 squared. So let's call this e to the 2 over 4. Okay, so if we were to sub this in down here, even if we sub this into the full equation, just to show us the steps, we would get e squared over 4 equals 0 times x plus b. Well, this goes to 0. E squared over 4 equals b. So that works. So our equation is, okay, y equals 0x plus e squared over 4, or simply y equals e squared over 4. This is the simplified version.